Do I start?
Okay, so then welcome everyone to the Culture Seminar. It's my pleasure to introduce Herwig Hauser, who will speak about Frobenius method for linear differential equations. Yeah, please, Herwig.
Thank you very much for the invitation. So this will be a very basic and elementary talk because I got to know Frobenius method by reading his original article from 1873. And it's not so easy to find there what he is really doing. I mean, the notation is kind of strange, but it's a very, very smart and accurate article. Of course, it is posterior to the article of Lazarus-Fuchs from 1866, who introduced the concept of regular singularities and characterized those equations which have regular singularities and moderate solutions. So I will try to give you first the idea of Frobenius, which is very simple afterwards, but that's always like this. Many ideas are afterward not so complicated. And then I will try to show you why we could have invented ourselves this method, yeah, and to put it in a more conceptual framework where you see that it appears naturally. Okay, so I have to recall a little bit the setting. All of you know, but just to fix the notation, we consider the differential equation Ly equals 0, which I will write like this. Zero. And my coefficients AI will be, let's say, in the ring of germs of holomorphic functions at 0, or if you want, they are formal power series, so we could take here pure modes, the complex numbers. All settings are fine, whatever you prefer. So everything is local at 0. We are only looking at local solutions and their shape and quality. So this is a homogeneous. Homogeneous in the sense that there is no term independent of y, linear, ordinary, differential. And Fuchs in his paper asked whether one can characterize those equations which have kind of nice solutions locally at 0. Yeah? Solutions in neighborhood. So he introduces the concept of singularity. Because we are familiar with this. So singularity will be a point where the quotient AI over AN. So if you divide by the leading coefficient and you look at all these quotients, the singularity will be a point where this has a pole, let's say, a 0 for at least one time. Otherwise, it's a non-singular point, and then if 0 is non-singular, then Cauchy-Kovalevskaya applies to find holomorphic solutions. So, of course, a basis of n solutions. So, Fuchs himself calls the singularity regular. Solutions grow moderately. So he starts out at the origin. There he will have a non-singular point, so he can construct his holomorphic solutions, and he continues them going inside into the origin. And the condition of having a regular singularity is that the solutions grow, let me say, moderately as it goes to 0. So moderately can be made precise in the sense that they go at most polynomially. or at most polynomial. Write down x to the minus k y of x remains constant. Now, of course, you know that we don't only have holomorphic solutions at a singular point, we will also have logarithms, and logarithms will precisely satisfy this condition. And Fuchs succeeded to characterize regular singularities in terms of the order of vanishing of the coefficients of your differential equation. It's a very simple formula, comparing the order of an with the order of the other ai, and this is known nowadays as Fuchs criterion. So now please let me know if I put this down and take the other one. Looks right for you. Let me check. It's okay like this. You cannot see the, but in any case you are familiar with it. Yeah.
Yeah, it looks fine. Good. Thank you.
So the local solution 0. We have a holomorphic. I am at a regular singularity and the logarithms appear. And what I want to explain to you today is why the logarithms appear and how much of the logarithms appear. You know that there will be certain powers of the logarithms, and to determine these powers, that's a little bit tricky. And actually, there are two reasons why we will have logarithms in the solutions, and the two reasons are completely different. So I'll start with the baby example. I start in the opposite way. I start with log of x, and then we get the differential equation xy prime equals 1. Now this is not homogeneous, so we derive another time, we get xy prime y prime 0. This is now, let me say, called this of y. This could be the differential equation defining just the usual logarithm, but we see that it has order 2, so there is a second solution. So y1 will be just a constant, and y2. So that's already interesting, even so easy. When a logarithm appears as a solution, you also get a monomial here. So, of course, here you cannot avoid, with this equation here, you cannot avoid considering logarithms. What about log square? So, of course, that's what you do when you give a class. You yourself, you choose your solution, find the differential equation, hide away the solution, and then you tell the students to solve. No, we do it exactly this way, and we get n of y. Now we get already order 3, x squared y triple, 3 x y double prime, y prime 0. So y1 is again a constant. This one will be our last solution, and in between we also have log of x as you verify immediately. So that's a situation where the appearance of the square of the logarithm forces the first power of the logarithm to appear as well. Okay. So of course, people at that time did a lot of computations and we knew all these solutions. If you want to do an exercise, what about log x? So find so that's not very difficult, but you will realize that it is not linear. It will be non-linear. And then you could try to find a linear equation, but there does not exist a linear equation with holomorphic coefficients. There only exists a linear equation where a logarithm appears as a coefficient. But if you want to be in the setting I presented before, it does not exist, and that's not so easy to prove. Okay? Actually, you would need the whole theory of Fuchs to prove this. Yeah? Does not admit linear differential equation. Okay. So that's kind of warm up. Now I have to erase for a moment. Excuse me, somebody else has a class in this room, but I have to convince the person to move to another room. So we can continue.
Soll man Zettel herhängen, vielleicht, weil sonst geht dann jeder rein.
Ja, aber
Ja.
ich bin mit dem Vortrag, ich kann es nicht. Excuse me, I'm back again. So let me give two interpretations of the method of the trick, or the idea of Frobenius. Now we take a differential equation with a parameter with the x, y double prime plus 1 minus t, y prime equals 0. So if we take t equals 1, we get what we had before. We get y1 equals 1, y2 equals x, no longer solutions. And now, if t is non-zero, same argument, we get y1 equals 1 and y2 equals t. Okay, now this has to be interpreted, of course, suitably. T is a complex number, but you can interpret it outside the origin, of course. Okay, and now we ask where this goes to when t goes to 0. That's what interests us. Okay, in order to get back the equation we had before. Okay? So this would go to x to the power 0, which would be the same. y2 goes to y1, and we miss the second solution. Miss at t equals 0. And now you do the following. You look at the derivative. You take the limit t goes to 0, x to the t minus 1. You take the difference of these two divided by t. So this is the limit 0 over t. You write x to the t as you should, as an exponential, x t of x 1. Now this will start with the 1, which cancels with this 1. And the linear term here will be just t log x divided by t. So you get limit t goes to 0, t log x plus terms of t, and this gives you log x. Well, I think even though simple, this is very interesting because it tells you when two solutions come together and you lose having a whole basis of solutions, then you just take the slope of this function at the point and you get a second solution. Okay. Now, of course, there's nothing deep behind, it's just a simple computation. Frobenius formulated in a different way. His idea was, of course, to consider this exponent here, which takes a certain values as a variable. Okay. Differentiate effective solution. E is reference to the exponent. But at that time, people did not talk about variables. I mean, they had the concept of coordinates, but he is saying, let's take it not fixed, but let it move on a circle in the complex domain, and then we derive as okay. So this equation here is an example of an Euler equation. So Euler equation would be L equals some Ci xi y del I. Okay, so here the shift, the difference between the exponents I minus I is 0. Shift is 0. Okay. In this situation, and that's the first step which has to be considered, if you plug in x to the t, we get trivially L of xt. Now this, such an Euler operator, maps monomials to monomials, but you get a coefficient. This is the initial polynomial. Which can be easily computed, of course, from the expansion of L, from the Ci. And in the example we have here, if t is 0, you will realize that chi of t has a double root. Yeah? In the example,
so we have a hard time reading the board. Would you mind writing a little bigger?
A little bit bigger.
Yes, writing bigger. Thank
But
you.
in the example, t equals 0 is a double root of chi of L here, because chi of L is just t squared. Okay. So can I think I will erase here, if you don't mind. Don't see this anymore. Now you observe, if you look here at this equation, and this appears almost implicitly like this in the paper of Frobenius, L does not depend on t. We consider t now as a variable. L does not depend on t. Here the terms depend on t. Now, if you differentiate this equation with respect to t, if you apply dt to star, you will get L it is commute with L, so we get dt equal, and here we will get chi dt. Let me write first chi prime L e times x t plus chi L t I'm not happy. T. Just check. Yes, and now if you take t equal the root of chi of t of multiplicity you will see that both terms vanish and we get L of dt. Because as t is at least a double root, also the derivative vanishes. And this is, of course, t times. So either you guess that you will have a logarithm or you apply this method. Okay, and from this simple trick, Frobenius reproves Fuchs' theory in a different language and in some sense more precise and with less complications. Okay, so that's here if you have, let's say, multiplicity 2 in general. And again, L Euler operator. And let me now row for a local exponent. And row, so local exponent means, of course, root L. Then we get solutions x to the row log x to the row log x to the power m row minus 1. So that's the first setting where logarithms appear, and they have to appear. Whenever you have multiple roots of your initial polynomial, you must have logarithms. But it could be that the multiplicities are all just one, so all the local exponents are simple roots of the initial polynomial, and nevertheless you get logarithms. And this has a different reason, which I will try to explain you now. So I would like to call the phenomenon behind resonance. And you have certainly heard about it. This is a case when two local exponents differ by an integer. Resonance. So now we pass on to an operator which is no longer Euler operator, so this would be the Euler operator, which I call also the initial form.
Could you write a bit bigger, even bigger? Could you write a bit bigger?
Yes. So this would be, without loss of generality, I can assume that the initial form has shift 0, as mentioned before, and T with an operator if positive. Okay. So the idea is now to interpret your differential operator as a deformation of its initial form, and the initial form is an Euler operator. And to solve Ly equals 0, solve L0 by equals 0, and lift. Now it should be better. I write a little bit larger. This is the solution. So that's of course a general principle. Whenever you have a perturbed system of equations or scalar equation, then you can define in a suitable way an initial approximation. L0 will be an approximation of L. There are two steps to do. You solve first the initial problem, and then you lift to a solution of Ly equals 0. Okay. So assume now that we have two local exponents, just two local exponents. They are defined just in terms of L0 because the initial polynomial only depends on L0. So let me call them sigma and rho. And we distinguish two cases. If rho minus sigma is not in Z, so if the difference is not integer, then solutions y1 equals x sigma f of x, y2 equals x rho g of x, f g is O holomorphic. Okay. There is no problem. You take the monomial solutions of the Euler operator equation and then you lift them. I will explain in a moment how you lift them. But if rho minus sigma belongs to Z, and without loss of generality, I can assume that rho is larger than sigma, then logarithm may appear, but need not. So I will try to describe the situation, how you prove when, or how you check when logarithms appear or not. I'm sorry that I have to erase again, but I think you got this. And what I'm describing now is implicitly contained in the papers of Fuchs and Frobenius, but it was not obvious how to extract it from there. And it is the following normal form theorem. Then we take L equals to L0 minus T. And I consider just two local exponents, rho minus sigma. First, we assume that the difference is not in Z. Then the situation is relatively easy. We define function space F, which will be our space where we search our solutions, x sigma O plus x rho O. So if you do it formally, then you could take here formal house here is. But of course, sigma and rho will be any complex numbers. Now, if you look here, as the difference is not in Z, this is a direct sum here. Right? Okay. Now, you take L0 as an operator from F. As L0 will kill x to the sigma and x to the rho, it will map F to x times F. But x times f is just x sigma plus 1 times this one, plus x rho plus 1 times this one. So this is easy to show. Now, the kernel will be given just by x sigma and x rho. So if you take it now in xf, then it is bijective. Easy to prove. As it is bijective, you just continue. You observe that t of f will lie inside x of f because it has shift larger than 0. So you can now write L equals L0 minus T. You just factor L0 and you get the identity of F minus, what do we get? Here you take the inverse of this isomorphism. Here I will denote it just by L0 inverse, composed with T. Here I mean the restriction to XF. This is well defined. And that denotes L composed with U. And as you have here something which is the identity plus something of positive shift, it's not hard to show that U will be from F to F. So you have two cases. Either you have the convergent holomorphic case, where you prove this one using the fact that the singularity is regular, or you just work in the formal power series setting, then you don't even need the regularity. Okay. But then, when you are done, then if y of x is the basis of solutions of L0y L0 gets solutions U inverse y of x of Ly. So this is the case outside resonance. And if you give me, still have a little bit of time, the case of resonance will be more interesting. Here you see, as U is an isomorphism which is given in a very simple manner, the inverse will be just the geometric series in this operator. You will see that here the U inverse will send holomorphic functions to holomorphic functions. So you end up with your solution in that space. Okay, you keep convergence. Keep holomorphic. Okay. So this proves everything, except that I did not prove that this is an isomorphism. But you can almost do it on your own. Now, B, if rho minus sigma is in Z, and I assume that the difference is positive, then this argument fails. This argument fails for a stupid reason. If you look here and here, now sigma and rho have integer differences. Here maybe you see it best. So this whole space here will no longer be a direct sum, it will be just this space. So F will be x sigma O, respectively x sigma Cx. These two collide in our function space, and it is too small to contain all solutions for the following reasons. The L0 from F goes again to XF as before, but as you convince yourself easily, the x to the rho will be killed by L0. Okay, but it is inside here. This one contains now x to the rho, but it does not appear in the image of L0. So it's no longer surjective. So So you cannot restrict it to a subspace to get an isomorphism, and you cannot consider this perturbation anymore. Okay. So that's just that's not a matter of taste, it's just like this. So that the escape from this situation is the following: you enlarge f either by introducing logarithms. We do it by just using a new variable. So let me erase for the last time. So in the case of resonance, we take a differential ring which is larger than just the one before. We find mu f equals x sigma c O, and then you take polynomials in the new variable z, and then shall play the role of a logarithm, so you define z prime equals 4x. Now you do the same business as before. It's like same procedure. We get a 0 from f times f. But let me just check for the computation. This trick with the logarithm will produce now our x to the row. Why? So name this L0 is now surjective. That's easy to prove. I leave it as an exercise. Or maybe I even write it. L0 x row z, x row 1 over x plus chi of row x row z. And this is just x row minus 1. And if you then if you multiply it with x, you get x row. Okay. So this is please check it on your own. So I conclude here with the normal form theorem of this space. So you take again L equals L0 minus T, and rho sigma local exponents. You can generalize it, of course, any number of exponents with any multiplicities. Rho minus sigma z plus as before. Then the same procedure as before, L equals L0 composed with U from F. And again, you can describe the solutions using just the pullback by U of solutions of L0. So I give you a small lemma at the end. How does this relate to the trick of Frobenius? Where does differentiation appear? And I can show you this now for L0. If you apply this to an arbitrary x to the t, z to the I, now we are inside here. Okay, we have a monomial in x and a monomial in z to the power I. And you will get xt. Again, L0 is Euler, so this is homogeneous. You get chi of t, zi, but then you get more terms. Before, in the earlier case, you just got 1, plus now you get chi prime of t I z I minus 1 plus, in this So you get a kind of Taylor expansion of your Euler operator, and this goes up to 1 over n factorial by n derivative, which usually we don't need, by falling factorial n z. So this tells you precisely how you operate with Euler operators on this large space, and it is a basis to prove here the necessary properties to get this. Okay. I apologize for the technical inconvenience, but I could not avoid it, and thank you for listening, and that's it.
Thank you very much. Let's thank the speaker. So yeah, please questions. Unmute yourself and ask, or type them into the chat. So let me start. So what, if I understand correctly, right? So if we have integer difference between the exponents, then we may or may not have logarithm, right?
Right.
So,
yes.
But then which of the behaviors is generic? So I take certain space for this perturbation t, let's say polynomial fixed degree, and which I will see more often, or probability 1, I guess.
Yeah, so the generic case will be that logarithms appear because you will, if the image here, now if your L0 goes from here to here, but the t, which is hard to control, these are the higher order terms of the operator, they may go into the spaces, they will in the image, they will have z's. Yeah, and if these cancel by chance, then you will have an apparent singularity and no logarithms. Yeah, but you cannot give an explicit closed criterion to say in this case I have no logarithms, and in another case I will have. Yeah, for the first phenomenon, you can read it on the multiplicities of the local exponents. Then you just look at Euler equations, but here it's somewhere hidden, and it could be that when you iterate, when you construct these automorphisms, you have an algorithm to compute the solutions. And it could happen that for 10 minutes you don't get logarithms and suddenly a logarithm appears. It seems that this cannot be really controlled here. Yeah.
I see. Yeah, thank you. Other questions? You can unmute yourself and ask, or type them into the chat.
I would have one.
Yeah, so Sebastian, please.
So if you take a look to nonlinear differential equations, you know from, you have a similar procedure. It's called Newton polygon method, but yeah, it reminds a lot of what you presented today. And after a finite number of steps, you will obtain a linear differential equation which determines the behavior of the solutions. Okay, so now, or the problem for this is that the Newton polygon method is formulated a bit complicated from time to time to follow for people. So I would wonder whether your formulation or what you presented today could help there and might lead to some more algorithmic methods.
Yeah, of course, implicitly, you also have the Newton polygon lying behind, because your iteration steps, when you, in order to compute the solutions here, you have to invert u, and this is the algorithm. And this algorithm will, of course, read implicitly the Newton polygon. Yeah. So, of course, this is just a linear case, but as Sebastian, you know very well, there are many procedures to linearize, and you do it, I mean, in your research, many ways to linearize first, and then maybe to, once you have linearized, you can look at the initial form itself. Yeah. So it's not so much important whether the original equation is linear or not. The key point is whether you can isolate a part of your differential operator which dominates the rest of it. Yeah? You need that the perturbation term is sufficiently small. If this perturbation term is linear or non-linear often doesn't make such a big role. Of course, the non-linear case is more complicated because the estimates are more hard to control, but it's the same philosophy. Yeah. What is behind essentially in the nonlinear case is the constant rank theorem from differential geometry. Yeah. But maybe just one word. This here applies also for irregular singularities. Yeah. This normal form holds also, you just get formal solutions, but you don't get sufficiently many because for having a regular singularity means that the order of the initial form equals the order of the operator L. And then you get, as you take all the solutions of L0 and you lift them, you immediately get the basis of Ly equals 0. If for an irregular singularity, you only get some solutions, but not the whole basis. But then you can iterate the procedure by multiplying your solutions with an exponential to the power 1 over x to the r. And then you can apply again this normal form theorem to construct all formal solutions which will now have essential singularity certificity. This is forthcoming work of a student of mine, Nikki Merkel.
Thanks.
Other questions? I would have one more. So in the abstract of your talk, you alluded that like modern language would allow us to see the Frobenius method easier. So do I understand correctly that you meant this formulation in terms of maps, or what was exactly the kind of the magic stick of modern language?
The reformulation of Frobenius trick lies in the Taylor expansion of the Euler operator once you extend it to a large ring. Yeah. There you see very nicely is the derivative of the initial polynomial here. Yeah. So all this is characteristic 0 case. Yeah. In characteristic P, my student Florian Filzin has developed a version of the normal form theorem which gives the same result, but in characteristic P, things are much more complicated because the map L0, even enlarging by one variable, need not be surjective. So what you do in characteristic P is you have to add here a countable number of new variables Zi, and then you get the same result, but you have infinitely many variables, and these infinitely many variables Zi will correspond. The first one will correspond to the logarithm, the second one corresponds to the logarithm of the logarithm, and so on. So you have iterated logarithms appearing, but of course in characteristic P they don't make sense. That's life.
Other questions? Okay, then let's thank the speaker again.
Thank you for your interest, and I'll join you next time again for the next lecture.
Oh, and I guess yes, many of the I guess all people in the audience have received the advertisement that Herwig will also teach a course, I guess, around these topics online.